What we do in life echoes in eternity. Is this just a fancy line, or is there some scientific truth in it as well? The answer is yes, and it is explained by the concept of gravitational memory. Imagine the universe as a giant notebook, each page filled with stories of cosmic events. But instead of ink and paper, these stories are written on the very fabric of space-time itself. Every collision, explosion, and cosmic event leaves an indelible mark, one that could last forever. This is the core idea behind gravitational memory. Gravitational waves, the ripples caused by massive objects like black holes or neutron stars merging, don't just pass through space, they leave a lasting imprint on space-time like a footprint on wet sand. The question is, how can we read these cosmic footprints, and what do they tell us about the universe's history? To understand gravitational memory, we first need to explore the concept of gravitational waves, which were predicted by Einstein over a century ago. These waves are like the universe's way of communicating major events. But it wasn't until 2015 that we finally heard the universe's first whisper, thanks to the groundbreaking work of the LIGO, Laser Interferometer Gravitational Wave Observatory. This moment was like tuning into a new radio station for the first time, one that broadcasts not in sound, but in the ripples and stretches of spacetime itself. Gravitational waves are often described as ripples in spacetime, but what does that actually mean? Picture spacetime as a massive, calm pond. When you toss a stone into the pond, ripples spread out from the impact point. In the cosmic sense, these stones are huge events like black hole mergers or neutron star collisions. When these objects crash into each other, they cause disturbances in the fabric of spacetime itself, sending out ripples. These are gravitational waves. Einstein's theory of general relativity first predicted these waves in 1916. According to his theory, massive objects don't just move through space, they bend and twist spacetime around them like a heavy ball placed on a trampoline. When these objects move rapidly or collide, they create ripples that spread out at the speed of light. However, these waves are incredibly faint. Imagine trying to detect the ripples from a stone dropped into a pond the size of the entire universe. For decades, scientists doubted we'd ever be able to detect them. But in 2015, LIGO achieved what many thought impossible. It picked up the faint ripple caused by the merger of two black holes over 1 billion light-years away. This was a monumental discovery, akin to seeing the splash of a stone in that cosmic pond for the first time. It confirmed that Einstein was right, and it opened up a whole new way of exploring the universe. So, why do these gravitational waves matter? They give us a unique window into the most violent events in the universe. Unlike light, which can be blocked by dust and gas, gravitational waves pass through everything, carrying information from events that might otherwise be hidden. They are like cosmic postcards, sent directly to us from black holes, neutron stars, and other massive objects. The gravitational waves are the keys that give us access to the memory of the universe called the gravitational memory, is the lasting distortions in spacetime caused by significant cosmic events. When gravitational waves pass through spacetime, they create not only temporary ripples, but also permanent changes. This concept goes beyond the idea of waves dissipating. Instead, certain events leave behind a trace, a subtle, lasting mark on the structure of spacetime itself. The reason gravitational memory occurs is due to the non-linear nature of gravitational waves. These waves interact with spacetime in such a way that, after the initial disturbance, the spacetime does not return entirely to its original state. Instead, a faint but permanent deformation remains. This is what scientists refer to as gravitational memory, an enduring signature of the cosmic event that caused the gravitational waves in the first place. These permanent changes, although extremely small, can offer insights into the events that created them. Black hole mergers, neutron star collisions, and other massive events leave a detectable imprint on spacetime. The memory effect is faint and difficult to measure, but its existence provides a new layer of information about the universe's most violent occurrences. The study of gravitational memory not only enriches our understanding of cosmic events, but also opens the door to new questions. For instance, these lingering distortions in spacetime might contain information about the physics of the objects involved in the collision, such as the mass and spin of black holes or the nature of neutron stars. Gravitational memory could also play a role in answering some of the more fundamental questions in physics, including the nature of space and time itself. As our technology evolves, so will our ability to observe these permanent imprints left by the universe. Gravitational memory presents a frontier where we are just beginning to scratch the surface of what these cosmic remnants can teach us about the underlying structure of reality. The search for gravitational waves began long before their eventual detection in 2015. One of the earliest pioneers was Joseph Weber, who in the 1960s built detectors aimed at capturing these elusive signals. Although his devices didn't yield concrete evidence, his work laid the groundwork for the future, inspiring advancements in both detection technology and theoretical physics. At the time, many physicists were doubtful that we could detect such faint disturbances in space-time. The technology simply wasn't advanced enough to capture the tiny shifts that gravitational waves create. However, Weber's bold attempts sparked new interest, and gradually the field of gravitational wave research evolved. Physicists developed more precise models predicting when and where these waves could be detected. It was through these early efforts that the idea of the gravitational memory began to take shape. Now the question arises of what actually triggers the creation of gravitational memory. Gravitational memory is linked to the most violent and energetic events in the universe. One key source is black hole mergers, where two black holes spiral inward and eventually collide. The immense gravitational forces involved in such events distort space-time to a degree that leaves a permanent imprint. Similarly, neutron star collisions generate powerful waves that create lasting effects. These collisions often release both gravitational and electromagnetic energy, contributing to changes in the fabric of space-time. Their detection provides a rare opportunity to study matter under conditions that cannot be replicated on Earth. Even less frequent but equally impactful are supernovae, the explosive deaths of massive stars. The sudden release of energy in these stellar explosions causes disturbances in space-time, albeit on a smaller scale compared to black hole or neutron star mergers. However, the events can still contribute to lasting changes that reflect the intensity of the explosion. These extreme cosmic occurrences provide valuable data not just about gravitational waves, but about the very nature of space-time itself. By studying them, scientists can extract detailed information about the physics of these collisions, advancing our understanding of how the universe functions on the largest and most violent scales. Gravitational memory offers profound implications for our understanding of the universe. One area where it could provide answers is the black hole information paradox, a long-debated question in physics. When matter falls into a black hole, where does the information about that matter go? According to current theories, the information seems to disappear entirely, but gravitational memory could offer clues that some trace of it remains imprinted in space-time. Another area where gravitational memory may play a role is in the no-hair theorem, which suggests that black holes are simple objects defined only by their mass, charge, and spin. If gravitational memory exists, it could indicate that black holes leave behind more complex information than previously thought, challenging this long-held theory. This opens the door to understanding how black holes interact with space-time in ways we have yet to fully explore. Beyond black holes, gravitational memory can act as a form of cosmic archaeology. Just as fossils tell us about Earth's ancient history, these lasting imprints in space-time could reveal details about cosmic events that occurred billions of years ago. By studying these distortions, scientists could uncover the hidden history of the universe, events that may not be visible in other forms of observation, such as light or radio waves. As we delve deeper into this area of research, gravitational memory could even help us understand fundamental mysteries like dark matter and dark energy. These forces, which make up the majority of the universe, remain largely invisible to us, but the gravitational imprints they might leave behind could offer new insights into their nature. The future of gravitational memory research is filled with exciting possibilities. While current technology is limited in its ability to detect these permanent distortions, advancements are on the horizon. Projects like LIGO promise to dramatically increase the sensitivity of our instruments, bringing us closer to directly observing gravitational memory. Positioned far from Earth's background noise, LIGO will be capable of detecting smaller and fainter cosmic imprints, potentially uncovering new events we've never observed before. As technology improves, we may also gain insights into unanswered questions in astrophysics. For example, gravitational memory could help us better understand the interactions between black holes and space-time, offering fresh perspectives on the nature of gravity itself. This research could also provide a deeper understanding of the large-scale structure of the universe, shedding light on how cosmic events influence the expansion of space-time. Theoretical breakthroughs are also likely to accompany these technological advances. As we collect more data, our understanding of gravitational memory's role in cosmic processes will evolve, potentially challenging or refining current models of how the universe works. New discoveries may even reveal unknown phenomena that could redefine our grasp of the cosmos. The road ahead is challenging, but the promise of what gravitational memory might reveal is too significant to ignore. Each step forward in this research brings us closer to unlocking the secrets of the universe's most dramatic and permanent events. The idea of a universe that remembers is not a new one. Long before the advent of modern science, ancient traditions and philosophies spoke of a cosmos that records everything, an eternal archive where nothing truly disappears. From the concept of the Akashic records in Eastern mysticism to the notion of a divine memory in various spiritual teachings, the idea that the universe holds a trace of every action, every event, has existed for millennia. Gravitational memory, as described by science, feels like the universe's physical manifestation of this age-old wisdom. We are discovering, through mathematics and observation, that cosmic events leave an indelible mark on space-time, a concept that resonates with ancient beliefs about the interconnectedness of all things. Just as sages and mystics once claimed that no word or deed vanishes without a trace, so too do black hole collisions and neutron star mergers permanently alter the universe's very fabric. But this raises deeper questions. If the universe remembers, what else might it be holding? Could they contain echoes of something even more profound, like the essence of life or consciousness itself? As science peels back the layers of reality, we are left to wonder, what other invisible forces are at work, shaping and recording the story of the cosmos? Are we too part of this cosmic memory, leaving behind traces that exist long after we're gone? And if the universe holds on to its history, does it also remember us? These questions invite us not only to look outward into the depths of space, but inward, into the mysteries of existence itself, blurring the line between the scientific and the spiritual in our quest to understand the universe's timeless memory.